Let us look at question number 37, Set 2, Civil Engineering, GATE 2021. An elevated cylindrical water storage tank is shown in the figure. The tank has an inner diameter of 1.5 meters. It is supported on a solid steel circular column of diameter 75 mm and total height L is equal to 4 meters. Take water density to be 1000 kg per meter cube and acceleration due to gravity equal to 10 meters per second square. If the elastic modulus E of steel is 200 GPa, ignoring the self-weight of the tank, for the supporting steel column to remain unbuckled, the maximum depth h of the water permissible is asked in meters rounded off to the first decimal place. Students are encouraged to watch this NPTEL lecture cited below where this topic is handled in more detail. However, we will be looking at some fundamentals as we go on to solve this problem. Let us look at some fundamentals related to buckling. Let us consider a column which is hinged at the bottom and has a roller support at the top and is subjected to a load P. In case this P is less than the critical buckling load PCR, the column would undergo axial compression. And if the axial compression exceeds the compressive strength of this column, it would undergo a material failure. Now, in a case where P exceeds the critical buckling load, the column would no longer undergo axial deformation but would instead show buckling, that it would deform to this shape. Hence, buckling is a stability failure, and it should be noted that buckling can take place at loads much less than the compressive strength of the column, and it relates to the geometry of the column. Consider that this column is made up of a material which has a Young's modulus of E. The cross section has a moment of inertia I, and the length of the column is given by L. Then the critical buckling load PCR for this column is given by pi square EI by L square. It is to be noted that when P exceeds this PCR at the slightest disturbance, the column would buckle to this shape, which is called the mode shape, which could be either this way or this way. This formulation is basically applicable only for the support conditions where one end is hinged and the other has a roller support. In order to extend this formulation to a general formulation, we make the following modification, where L effective is defined as the effective length of column which participates in buckling, and this effective length depends on the support conditions. Now, for a column which is pinned at one end and has a roller at the other, the effective length is essentially the entire length of the column since it participates in the buckling. Hence, for this case, L effective is equal to L. Similarly, if we were to consider a column which is fixed at the end and has a roller on top and is subjected to a compressive load, the buckle shape of this column would essentially be like this. We can see that since this end is fixed, the slope at this end would have to be 0, and hence L effective in this case is derived to be 0.7 times of L. Similarly, for a column which is fixed at both ends and is subjected to a compression such that the support itself moves towards each other, the buckled mode shape would look something like this, where the ends are still arrested against rotation, and in such a case L effective is essentially half of L. And in the last case where we have a freestanding column which is fixed at the bottom end and free to move at the top, the buckle shape would be something like this, and in this case L effective is equal to 2L. The derivations for these values essentially come from comparing the length of these mode shapes with the wavelength of the sine curve which shows in the solution, and students are encouraged to watch the NPTEL lecture cited above for the derivations of these values. Hence, we can see that once we substitute L effective into this formulation, we can easily calculate the critical buckling load for any given configuration of supports. Let us come back to the problem at hand. Now it is given that this tank is filled with water and the permissible height h is asked so that the steel column at the bottom can take that load without buckling, which essentially implies that the weight of water column in tank has to be less than or equal to critical buckling load for the column. Now we can see that since this column is not restrained at the top and has a fixed end at the bottom, this would essentially show a mode shape like this, and this pertains to the condition where one end is fixed while the other end is free. Hence, L effective is nothing but 2L for this case. Further, we have been told to ignore the self weight of the tank itself, and we are only to consider the weight of water inside this tank. Now, the tank dia is given to be 1.5 meters. Let us say the height of the water column is h meters. The density of water is given to be 1000 kg per meter cube and acceleration due to gravity is given to be 10 meters per second square. Hence, weight of the water column is nothing but volume into the unit weight, which is 1.5 square pi by 4, which is the area, into the height into the unit weight, and this would give us the weight of the column in newtons, which would come out to be 5625 pi h newtons. Let us now calculate the critical buckling load for this column. Now we saw that PCR is given by pi square EI by L effective squared, which is nothing but pi square into 200 GPa. Converting that to pascals, it will be 200 into 10 power 9 into moment of inertia of the circular column, which is nothing but pi d power 4 by 64, and d is given to be 75 mm. Hence, we will substitute 75 into 10 power minus 3 power 4 whole divided by 64, and this entire thing will be divided by the effective length of the column, which we saw to be 2L, which is nothing but 2 into 4 meters, which is 8 meters. Hence, we will have 8 squared here, and this comes out to be 47903.22 Newton. Hence, for calculating the safe permissible height of the water column H, we can see that 5625 pi H, the weight of the water column, must be less than or equal to 47903.22 newtons. And from here, we can calculate H should be less than equal to 2.71 meters. In the question, we have been asked to report the height rounded off to the first decimal place. Hence, the height of the water column permissible in order to prevent the buckling of this column is 2.7 meters, and this is our final answer. Thank you.